I have the pleasure of introducing Seth Lloyd. This is a somewhat strange talk for the Center of Brains, Minds, and Machines because this has to do with quantum theory. But you know, it's great to have Seth, which is one of the nicest and most creative colleagues I have at MIT, and after all, the mind is quite a mystery, and um, quantum theory is quite a mystery. This is basically the argument.
But that does not mean they're the same,
used.
they're mysterious in the same way.
Exactly. And you'll explain in which sense maybe we can use one to understand some of the other. Seth.
Okay, thank you very much. It's a real pleasure to be here, though I must say I face this with some trepidation because I am going to be talking about things that happen in the brain. And I'm quite sure that pretty much everybody in this room knows more about this topic than I do. But since my lab motto is powered by ignorance, I thought I would go on. We were thinking of making bumper stickers, actually, but I figured maybe the Boston drivers wouldn't get the joke. Take it too literally. When I looked at the abstract and title I'd given for this talk, I said, wow, that sounds pretty wacky. And my purpose in giving this talk is to tell you a little bit about something that I've been learning about the last few years. Let's see if I can't find the right. Which is, as Tomasa said, I work primarily on quantum mechanics and on quantum computers. And I've been doing a lot of work on quantum algorithms for machine learning over the last few years to figure out new ways of trying to analyze data quantum mechanically. And one of these algorithms is to analyze topological features of data. So topological features are things about, a topological space is a space where you have a notion of adjacency, that things are next to each other. And topological features are things like the number of connected components in this space, or the number of holes in a space, or the number of gaps or voids. So topology is a very basic notion, and over the last 20 years, there's been a series of topological machine learning algorithms to try to learn topology from data. And there's a very good reason for doing this, which was explained to me by Michael Friedman, a Fields medalist who got a famous topologist. And he's the one, he coined the phrase, the mysterious phrase, topology is the discrete residue of geometry, whatever that means. I have no idea. No, I'll tell you what that means in the course of this talk. But the reason is that what is data? Data is information we gather from the world. And when we analyze the data, we're trying to establish relationships that are out there in the real world. But merely by getting the information and representing it, the data gives a distorted picture of what's out there in the world. And topological features, something like, the hole in a donut, are famously features that are invariant under continuous distortions. I remember when I was a kid reading this article in Scientific American, here is a donut, here is a coffee cup, they have the same topology. I was like, what? So, and as this kind of complicated looking article shows, people have been applying this to analyzing data from the brain. I'll actually explain what's in this paper. I'm putting this up for two reasons. The first is to show you that these methods look really fiendishly kind of complicated. This, by the way, is a paper. I had a terrible time learning these methods. Somebody told me I should learn about these topological methods, and I tried to read the papers and I failed. And then I tried again and I failed. It's like a novel, right? You read a novel and you just don't make it past the first 100 pages or first 50 pages. But I know from reading novels, eventually if you try enough, you can eventually sometimes succeed. And I finally enlisted the help of a bunch of people who are much more mathematically sophisticated than I am. One is Francesco Vaccarino, who's one of the authors of this paper, to help explain this to me. And then once they'd explained it to me, I realized that I could actually make quantum mechanical versions of these algorithms. By the way, the quantum mechanical versions of these topological algorithms have the feature that they're exponentially faster than the classical versions for a reason that I'll explain in a bit. But I'm just putting this up to show, this is a kind of paper where you start looking at the things like this, you go down this list of features that are going to be discussed, and you get down to the kth homology group, and you say, okay, forget it, At least that would be my my take on this. There's an old I sometimes read papers. There's an old Peanuts cartoon where Linus is reading Brothers Karamazov, and Charlie Brown says to Linus, "But what do you do with all those long, complicated Russian names? Because everybody has like 5 different names. You can't remember who they are." Linus says, "Oh, it's very easy. When I get to one, I just bleep right over it." So this is often a good way to read a paper. It's like you get to some equation you don't understand, just bleep right over it and hope it will become clear. Anyway, this is a paper where, it's very specialized to this topological analysis. It's all about homology groups and things like that. Here are pictures of these, appearance of holes, closures of holes. I'm really showing this to show you this paper, despite the fact that it probably can only be understood by about 50 people in the world, and I don't think I'm necessarily one of them. It has an awesome graphic in it, which was downloaded hundreds of thousands of times, and it was Wired magazine's best scientific graphic of 2015. So what is this graphic? This shows you the kind of information you get out of looking at topological processes, topological analysis of processes. Here is this data is functional MRI data from the brain, divided up into 256 segments. You get a notion of adjacency of different neural sectors by looking at the correlations between the data. So if two of these sectors are highly correlated with each other, even if they're far apart in the actual physical brain, then you assign them an adjacency. You say they're adjacent. And then they did this analysis of the brain. The picture on the right is the topological analysis of the resting brain. And each of these little clumps represents, clusters of neurons or topological features, connected components. And then you see that the clumps kind of naturally divide up into 5 or 6 or 7 or 8 different thought processes, which are these different colors, which are characterized by some kind of connectedness structure. And this makes sense, like if you're just sitting with the resting brain, you've got a bunch of things going on in your mind at once, simultaneously. And the lines represent overlaps that connect these different thought processes to each other. It makes some kind of sense that, that you have different thought processes that are going on. Who knows? It's mysterious how they actually occur. And by the way, that's like, this quantum mechanics is mysterious, the brain is mysterious. To say, oh, they must be mysterious in the same way, I call this the Penrosian fallacy, right? Gravity is mysterious, quantum mechanics is mysterious, the brain is mysterious, consciousness is mysterious. They must all be the same thing. This is simply not true, okay? Though I will perilously closely to talking about quantum mechanics in the brain in this talk. I should say right at the start that I don't believe that there's any fancy quantum mechanical coherence or anything like that that's going on in ordinary neural function, except possibly at the level of individual synaptic receptors, where there is evidence that in receptor dynamics and molecular dynamics and receptors, quantum mechanics plays a role. But don't worry, I'm not going to claim that our thought processes are quantum mechanical. So this picture on the left is the topology of the ordinary resting brain. And the picture on the right is taken from the same group of subjects after they'd taken psilocybin. Magic mushrooms. And what can I say? Whoa, everything is connected. Wow. I think this explains a lot. Anyway. I thought you would enjoy this because what is not to like about this? My God. So anyway, during this talk, I'm going to do the following. So I'm going to raise a question that has been noted. I came to these ideas kind of circuitously. I've been working on these topological algorithms for the purpose of making quantum algorithms that did exponentially better than the classical ones. And then a few years ago, a reporter called me up to ask my opinion about what's called the quantum question order effect. Okay, who here has heard of the quantum question order effect? I see people who have, yeah, some people have, yeah. So this is a very interesting effect, and not without controversy. Some papers written about it say it's absolutely crystal clear and it's absolutely the case. Others say, well, maybe it's not so clear. But it comes from a very simple observation. So when you ask people questions, the order of the questions matter. So if you ask them the questions in one order, you'll get different probabilities for the answer than if you ask them questions in the opposite order. That makes perfect sense because, once you've answered the first question, your brain is in some state corresponding to just having answered that question. And then when you answer the next question, whatever neural processes are going on then will come into play when you answer the next question, and vice versa. So it certainly makes sense that, that when you ask people questions, that the probabilities that they answer with are not just, they depend on the order. Now in quantum mechanics, it's also the case that asking questions depends on the order. If I measure first momentum and then position, I'll get different answers than if I measure probabilities for the results if I measure first position and then momentum. And this happens because in quantum mechanics, there's a very specific mathematical structure, which I will now tell you. So in quantum mechanics, I have the states of a system. So for instance, I have a state which could correspond, it's nice and quantum mechanical, right? It's like if you are not, who here has a background in quantum mechanics? I know some people do. Okay, who here doesn't? Right. Who here does and doesn't at the same time? All right, those are the true quantum mechanics, right? So if you don't have a background in quantum mechanics, then when you put these things called Dirac brackets around something, it means it's a quantum mechanical thing, right? There are actually two ways to indicate things are quantum mechanical things. So one is to take a letter and change it to a Q. So a while ago, I worked with people at Google on a project called Krugel, right, which is a quantum version of Google. And now Google has an actual quantum artificial intelligence lab. I've been working with people there, and here's their logo for the quantum AI lab at Google. In fact, they've got an agreement from Sergey Brin that nobody else in Google is allowed to use the word quantum, because the word quantum gets used all the time for just to say that something is kind of cool. We made a quantum version of the Netflix algorithm. So it's kind of a matrix completion algorithm. It's like you watch these movies, you might enjoy these other movies. And we said, oh, this is great. We can call it the quantum Netflix algorithm. But then I Googled quantum Netflix algorithm. And it turns out that the algorithm that Netflix created themselves for this, they call their quantum algorithm. Even though it has nothing to do with quantum mechanics. So here is a quantum mechanical state. And this could be the state that says, OK, I asked my first question and I got the answer A. And it's a vector. It's just some vector typically in some rather high-dimensional complex vector space. OK? And we could even, I can just write it as that if you don't want it to look quantum mechanical. But it looks quantum mechanical, so it's cool, right? And then suppose that B corresponds to answering the second question, to giving the answer B for the second question. Okay. Now, in quantum mechanics, the probability that I get B for the second one, given that I got A for the first question, is equal to the following thing. I'll write it in fancy form here. It's equal to this thing, which is just actually equal to B transpose. It's actually just, all it is actually really B transpose complex conjugate dot A quantity squared. So these states correspond to vectors, and conditional probabilities correspond to the inner product of these vectors squared. All right? But we note that this is also equal to the inner product taken in the other way squared, and that's equal to the probability of asking B first and then getting the answer A second. So if I asked the first question, got the result B, then the conditional probability for getting A, answer A for the second question, is the same as if I got the answer, given that I got the answer A for the first question, I got the answer B for the second question. So this is the order effect in quantum mechanics. I could make it fancier, but there's, you can talk about, measurements, et cetera. But this is the basic reason why this is a basic feature of quantum mechanics. You always get this particular form for the conditional probabilities. Now, the quantum question order effect in human beings is that, quite bizarrely, there's strong empirical evidence based on many studies. I think one of the papers I have looked at 70 studies with an average of 1,000 people in each study. So there are many people, there are many studies on this. It appears that human beings obey the same rule. The degree of accuracy to which this is true differs according to who's making the claims. And you look at the statistical analysis, and it's, there are lies, damn lies, and statistics. And then, but it does seem that something like this is going on. Yeah?
Why are you calling this order effect? You're saying two are actually equal?
No, because it's traditionally called this. It's traditionally called the quantum order effect. Yeah. That's why I agree that would be a better word for it. Oh, the order does make a difference. Absolutely. This is not. Yeah. This you can easily, because of. No. Okay. No. I better answer this question, right? So, this does not mean that probability of B first getting A then B has to be the probability of first getting B and then getting A. It's the conditional probability given this. That would be true by Bayes' rule, since P of A given B is P of B given A times P of A divided by PB by Bayes' theorem. Bayes' rule or Bayes' rule. These will be the same only if these probabilities are equal, which in general they're not. So it really is an order effect. Somebody else had a question, yeah. It was the same question. Okay, yeah. It's right. So the probability of first getting B, then A doesn't have to be the same as the probability of first A and then B. It's the conditional probability that if you got A, then you get B, is equal to the conditional probability that if you got B, then you get A. Right. So you can get quite bizarre effects out of this. And when your probabilities have this kind of feature here, there are a host of other kind of anomalous decision effects which don't obey the ordinary rules of probabilities. That many ordinary probability rules assume that P of BA is the same as P of AB. And you get all kinds of bizarre things like the probability of A and B people judge this to be higher than the probability of B, which can't happen with ordinary probabilities. But it can happen when you actually have this kind of projective structure. And there's, at least in the papers that I've read on the quantum question order effect, there are lots of ways that people actually try to explain these other issues as well, but they basically come down to this funny feature. And it's completely mysterious why human beings apparently have this feature as well. There's no good explanation for this. There's no real reason why human beings, sure, there's an order effect, but why should it have this funny quantum mechanical like structure? And it is not because, and the authors of these papers, thank God, they're not Stuart Hameroff and Roger Penrose, and so they're not claiming that this is because the brain is quantum mechanical and our thoughts in a quantum mechanical superposition, et cetera. But I would say that what it indicates is that it is suggestive that there might be some description of the thought processes and of neural processes that has some kind of vectorial description and that that these probabilities are in sense of, that you go to B given that you answered A is given by some function of the inner product between these vectors. That's what it suggests. And I'm going to make a proposal, which I have no idea if it's true or not, about that maybe what's going on is that these vectors are vectors that describe topological states of the way that the brain functions. That's what I'm going to propose. And I don't know if it's true, okay? But, and anybody's welcome to come up with their own, vectorial picture of brain functions and to argue that, hey, these conditional probabilities should depend only on, the inner product between these vectors. Because you see, that's what really is required for this quantum order effect. This quantum order effect, if indeed there's some dynamics which can be accurately described by, brain processes correspond to vectors in a high-dimensional space, and then it turns out that if you're in vector neural state A, that your probability going to neural state B is proportional to the overlap. It doesn't even have to be the overlap squared. It could be any function of the overlap. Then that would explain this quantum question order effect. And actually, when I phrase it in those terms, that actually sounds kind of plausible. And I will at the end of the talk, I'll give a specific model in which I'll argue that it's plausible. And it's a model based on work by my colleague Jean-Jacques Slotine in the mechanical engineering department. They had a nice paper about neural nets, artificial neural nets. And I'm trying to get them to test to see if this is true. So, yeah. So yeah, it's got to be not any function. Sorry, yes. So, yeah. Any positive function of this will do it, right? Because this is symmetric. The magnitude of the inner product is symmetric in A and B. Doesn't have to be. For instance, the square is what's called the Born rule. For some reason, in the literature, people always assume that these things obey the Born rule. It does not have to be that way. So if you happen to read some of these papers, you don't actually have to have this Born rule square here. That would be really, that's getting pretty hard to get. It just has to be some function of this. And that's, then, for instance, if these vectors are normalized to 1, then the inner product is simply a measure of the distance between these vectors. So I can imagine cooking up all kinds of models where, if I'm in state A, state corresponding to vector A, then my probability going to vector B is some function of the distance between these two vectors. That makes perfect sense. Anyway, I'll stop trying to talk you into it. I actually have difficulty talking myself. Maybe I'm more trying to talk myself into it. Okay.
That you ask,
yeah.
And it knocks a person into a brain state, and from within that brain state, there's a fixed probability that they would return A or B. If you're asking a different question, so A and B here, you're asking different questions. One of those is, are you more likely to buy Koch brothers products versus this? And the other question is, do you care about the Koch brothers' impact on politics or something?
Yeah, that's the kind of questions that they ask, yeah.
Which you might have fixed responses for those two answers because there's a lot of different brain states people operate in.
Right, that's right. But that in and of itself does not necessarily imply that this particular form. So I agree that a question order effect is clear, that just as you said, right? And I think I said a less articulate version of that a little earlier, that makes sense. But in addition, you need something more, which is that the probabilities in some sense obey this funny. Well, the probabilities, if you're in brain state A, that you go to brain state B, when you ask the question that can have answer B, is the same as the probability if you're in a brain state B that you go to A if you ask the question that corresponds to A, right?
And when you ask the second question, it's now overlaid on that brain state they're already knocked into.
Yeah, I mean, so the kind of models, for instance, in Slotine's paper, basically, there's a kind of there's some brain state, which is your neurons firing in a particular set of pattern, and then you ask a question. And now your brain is put in a mode where it has to give this answer or this other answer. So you're going to go, these are attractors of some complicated nonlinear dynamics. Okay, you're actually forcing me to give my argument for why this should be the case, but I'll do that anyway. Why not? In case I don't make it to the end. So there's some complicated nonlinear dynamics that's going on that you end up either in this attractor, B, or end up in not B. Okay. Now, what's weird about this, we know that there's complicated nonlinear dynamics, yet here there's somehow something very linear about this. What the heck is going on with that? But, you know, if the point here is that if your probability is some function of the distance from your original brain state expressed in this vector to here, to not B or to B, the distance from A to B and to not B is the same as the distance from B to A and from not B to A. That's what this is actually saying. So then I think that that actually makes some kind of a sense. And if you're just rattling around in some like weird nonlinear dynamics, which is what my brain does, and you have to end up in this tractor or another, then it makes sense that, you know, the further away this is, the less likely you are to go in it, and the closer you are to the other one, the more likely you are to go in it. Still, that's something that really has to be verified. This is not, I would say this is not at all obvious, even though I was trying to make it plausible. Right. Any other questions about the quantum question order effect?
The first one is, so is the motivation for entire framework which you propose just the observation that human responses to questions are not independent?
Actually, no. In fact, now you're forcing me to, because you asked the questions were asked in a different order from what I expected. You're forcing me to give my, to reveal my motivation for this talk, which is that actually, you know, there's a huge amount of data about how brains work. And I mean, the amount has exploded vastly, and it's going to continue to explode even more vastly. Now, how do we make sense of this, right? What is, you know, how do we make sense of what's going on with these very complicated systems with very large amounts of data? So you know, how do we find patterns of how thought patterns work? How do we make sense of what's going on? I'd like to argue, and I already argued for the case of data in general, but that for brain data in particular, these kinds of topological approaches are potentially that, you know, the topology is the general connectedness structure of anything, and the general connectedness structure of what's going on in the brain is probably a good way to go. And may I say that this is a well-established field of ordinary machine learning, and there are just off-the-shelf packages you can use to try to analyze it. You don't have to actually go in and read papers like homological scaffolds of neural functioning, and you don't have to know what the K-homology group is either. In fact, that was the big hump for me for getting over this. But so yeah, this in some sense, this quantum question order effect, I realized, having, you know, spent all this time learning about these topological analysis methods, is topological analysis methods, as we'll see, require you to describe topology in terms of vectors in high-dimensional vector spaces. How algebraic topology works. That's how these analysis methods works. So, you know, whether independently of anything about quantum mechanical in the brain, then you can describe the topology. In fact, you're kind of forced to describe the topology of what's going on by this vectorial representation. And this vectorial representation, and then I realized, while I was working on this last summer, I remembered this, you know, this reporter calling me and asked me to give some comment about, you know, quantum question order effect, which I was simply saying it's very important to note this is not a quantum mechanical effect, right? I realized, hey, this topological description already has this vectorial picture built into it. Maybe what's going on is the kind of thing we were just kind of discussing, but it's governed by this funny linear algebra. So that's why I came to this quantum question order effect. And I think it is kind of fun. So, and apparently it's an effect. Okay, now, so what I intend to do now is just to describe to you quite briefly how these classical algorithms work for analyzing topology. And this will be a little bit mathy, but and as you saw, the math looks hideously complicated but the actual ideas are, in fact, rather straightforward. And you know, when I actually finally got over the hump to learn what was going on, I realized that it wasn't as complicated as I thought. So I thought that, you know, I would actually tell you my brief understanding. I have a very crude understanding of this, which is good for pedagogical purposes. My crude understanding of what's going on with these topological analysis. If you're not interested in that's fine, then we'll go back in about 10 minutes or something like that. We'll go back to arguing about, you know, what might be, you know, what might be actually going on that's responsible for this quantum question order effect, which is just the kind of thing that you were saying. Okay? So are there any more questions about the quantum question order effect, or anybody else want to stop me, want to ask? You can delay me talking about algebraic topology, but you can't stop me. Who here, by the way, who here has studied algebraic topology? Okay, great. So we actually have people, and once again, probably guaranteeing that you know more than I do. This is actually I think this is actually a pretty cool technique. Once I finally understood it, it's like, oh, okay, that actually is pretty neat. So here's what these algorithms are supposed to do. So here's some data, okay? The data has a hole in it, all right? There's a hole. Of course, so how do we tell that? Because something's sort of strange, like if I look really close, it's all holes. Not a hole, right? And then, but if I like, you know, if I move back and I fuzz it out, it's like, oh yeah, look, that's a great hole. There is a hole, and then because I'm quite nearsighted, when I get back here, it's like, I just see some kind of blob over there, right? So the way that these methods work, the idea is that you want to analyze the topology of the data at different levels of fuzziness. And at different levels of fuzziness, then by using this mathematical structure of algebraic topology, which basically is just, all it is to get topological features by looking at big vectors in gigantic dimensional vector spaces. Which is why, by the way, we have super fancy quantum machine learning algorithms for them. By looking at it at different scales of fuzziness, if you have a feature, a hole, right? And a hole is something that belongs to this thing called the homology. A homology just means it's some topological thing that you can use to scare people with words like homology and cohomology and stuff like that, right? So the hole belongs to the homology, and the idea is that if it's some level of kind of fuzziness, you see a hole, you find a hole, and it persists over many levels of fuzziness until finally it goes away, that this hole is a real feature of whatever the thing was that you took the data about. Okay? So in fact, this theory is called persistent homology. Persistent homology. So persistent homology, the idea is that you analyze the data at different scales of fuzziness. At each scale, you find the topological features like holes, connected components, voids, gaps, etc. And then if you find a feature that persists over many scales of fuzziness, you say that's a real feature of what's going on. So these topological methods work in that way. That's what they're doing. Does this make sense? I mean, I think it seems like a wise thing. Yeah, and people have been doing the names associated with this. I think actually Michael Friedman, the topologist, actually developed some of this for a secret DARPA project in the 1980s. And when I gave a talk about the quantum algorithm, he got incredibly excited and gave me all these top secret documents, which was really fun. Done, but he just wanted to show that he'd done it first. And then his colleague Carsten Nielsen at UC San Diego then picked up on it and then developed this theory. There's a lot of people working on it over the last 25 years or so. Okay, so now how do we apply this measure of fuzziness? So the idea is we have a notion of distance between points. So these are between two data points, distance between two data points, I and j. I always draw my distances as little deltas like this because they obey the triangle inequality. So fine thing. So it reminds you of that. So we have distances, and we have a fuzziness scale. I'll call it a grouping scale. Epsilon. I call it epsilon because it starts small, and then it gets bigger. And so then the feature is we connect 2 points if within epsilon, if delta ij is less than or equal to epsilon. So I'm going to change this set of dots into a graph, okay? And so when epsilon is very small, I don't connect anything. But then when epsilon gets bigger, I start to connect, these points here, these points here, these points here, these points here. So as epsilon gets bigger, the first thing that happens is you start to create a bunch of edges. You also start creating little triangles. So when you have 3 points that are all within epsilon of each other, you create a triangle. And when you have 4 points that are within epsilon of each other, you create a tetrahedron. 5 points, you create a pentahedron or whatever it's called. I guess it has 10 sides. Okay, so start creating edges, triangles, tetrahedra, etc. And these things are called simplices, K-simplices. So a triangle is a 2-simplex. It's a 2-dimensional simplex. An edge is a 1-simplex. A tetrahedron is a 3-simplex. So as epsilon gets bigger, a simplicial complex, it's called a simplicial complex, I'm afraid to say, S epsilon emerges. I start connecting these points, and then what happens is at a certain point, when I start connecting things, I'm not going to connect everything here because I drew too many points, but at a certain point in this epsilon, when epsilon gets large enough, what happens is the hole will emerge. You'll see the hole, okay? Then if I start connecting points that are further and further away, what happens is actually the hole starts to go away, and finally, if I connect all points within the radius of this whole thing, the hole is gone. So I have what is a nested set of simplicial complexes. Complices, depending on how you want to say it. And this is what's called a filtration. So note, if a simplex is in the complex at some scale epsilon, when I make epsilon bigger, it's still in the complex. Now, so let's start counting, all right? The counting is going to get scary, but let's do this counting. So I claim there are 2 to the n possible simplices in the complex. So at any point, there will be some number less than 2 to the n. When I get everything is in it, then I have 2 to the n. And there's a simple way to actually see this. First of all, this is the power set. It's the set of all subsets of these, if there are n points. It's the set of any subset of these endpoints is a possible simplex. This is the set of all subsets is the power set. There are 2 to the n members in the power set, blah, blah, blah. But it's much easier to just see it in the following way. I can label a simplex just by putting a 1 there is if a vertex is in the simplex and putting a 0 if the vertex is not. So this is a one where 0.2, it's a tetrahedron with that it contains 0.2, 0.3, 0.5, and 0.7. All right? Does this make sense? It's a way of labeling the simplices in the complex. I could also give a list of vertices. So vertex 1, vertex 0, vertex 2, I0. Or VI0, VI1 up to VIK. Because note that a triangle is a 2-simplex, so a K-simplex has K plus 1 vertices. All right. So this, by the way, you can see that even for rather modest data sets, listing all the simplices in this filtration at each point epsilon can get very difficult. And if you look at the classical methods, people tend to focus only on things up to 2 or at most 3 simplices, because there are n choose k, k plus 1 possible k simplices. So for when I'm looking just at things like edges and triangles and things like that, it's not as bad. Our quantum algorithms actually nicely will handle everything very beautifully. Because the way that this works, and I think I'm actually tempted to describe this because I already introduced it, this quantum mechanical notation. I'll actually describe this in quantum mechanical notation. I'll show you why we can make a quantum algorithm that kicks classical topological butt. So the way that it works is, so algebraic topology. Anybody here colorblind? Is red okay for people? You don't have to admit it. So I don't see it. I don't see it very well myself. So how does algebraic topology work? So once I actually have a simplicial complex at some scale, I can now go ahead to identify the number of connected components, the number of holes, the number of 3-dimensional voids in the system, the number of very high-dimensional holes and voids. And these are these elements of this homology. These are the topological features of this data. So a component is, for instance, if we think about neural activity, we could say, and if these distances are given by correlations between neurons over time, then a connected component is a cluster of neurons that are talking with each other very strongly, right? And a 2-dimensional hole means that we have something that's going around in we have neural activity and signals going around in a topologically non-trivial fashion. And if there's a void, it means that, nothing's going on in there, okay? So these topological algorithms, just for data in general, the topological features that you get tell you something about what's going on in the system. Moreover, they're kind of a fingerprint for the data. That is, if I take the data and I mess around with it, it should still have, I deform it in the way that I described before, it should have the same topological features. They might just show up at different scales, at slightly different scales, epsilon, but topological feature that shows up and persists for many scales will also be there if I deform what this data is. So algebraic topology works in the following fashion. Map each simplex to a vector in a high-dimensional vector space. N of them. So I'm going to take the complex numbers raised to the 2 to the nth power. It's a big vector space. You can see how this gets combinatorially tough with the classical algorithms. But quantum mechanically, I'm going to do this in the following fashion. I just quantized it. Quantized this. I'm guiltily, because we're proud of this algorithm, I'm telling you how the algorithm works. Okay. So this is n quantum bits or n qubits. Now, don't get confused about that. This is not what's going on in the brain. This is just showing how you do algebraic topology in a quantum mechanical fashion. That's all I'm doing right here. So, right. So I used this is, by the way, the changing a letter to Q as in Q. I call that first quantization. Putting it in a Dirac bracket, I call the second quantization. Right, this is a quantum mechanics joke. Sorry. Not a very funny one either. So. Okay. Then there is now what you do, the way, as its name suggests, your analysis to find topological features can now be, you can find topological features by asking questions about linear maps on this high-dimensional vector space. And particularly, there's a linear map called the boundary map. I'll call it del K. The boundary map takes a simplex and it maps it to the sum. It's a vector now, right? It maps it to the sum of the simplices on the boundary. So for instance, if I have something that looks like, let's do it like this. Here's one, here's 3. This is a simplex. Here's something like this. Here's 3, 4, 5, 6. Here's a simplex 1, 2, 3. And here's a hole, right? Which is the kind of thing we're going to want to try to find using this procedure, and I hope I can explain this. But anyway, the simplex 1, 2, 3, it gets mapped to the sum of 1, 2. Remember, these are vectors now, plus 2, 3, plus 3, 1. But there's a sneaky feature about this. These are vectors. They sit in this vector space. And you actually alternate minus signs. So you actually subtract this one. You'll see why in just a second. So the boundary map acts on a vector like this. It's to take the vector vi0, vi1, vi. It goes to the one which is, I remove the first one. Then I remove the second one. Etc. up to, I'll do it like this. I'll write it like this. Minus 1 to the L vi0 dot dot. I remove the elf one. So this means I took it out. So it's just a map on a very high dimensional, a linear map on a very high dimensional vector space, a 2 to the n dimensional vector space. A 2 to the n by 2 to the n operator. And I can define it for each of these. And why, let me show you why this works so nicely. Why define such an object? It's the following. So suppose I have something like this. Okay. Now I apply this map to this collection of, remember, this is just a collection of simplices. There are 2, 3, 2 simplices here. 1, 2, 4, and there's 2, 3, 4. And I take the boundary map and I apply it to this. So I take the D2, apply it to this, and I get 1, 2, minus minus 2, 4, plus 4, 1. And I get plus 2, 3. Plus 1, 2, minus 2, 4, plus 4, 1. No, for this, because I start with the first label, which is 2. So it's 2, 3, minus 3, 4, plus 2, 4. And you see something, do you see what's going on? What's going on is rather nice, which is that the 2, 4s cancel. So all internal edges, or internal simplices, get actually go away to 0. So if I have a collection of connected simplices, then the boundary map will construct the simplices which are on the boundary of this whole collection. It's called a chain of simplices. All the internal simplices get counted once in one direction and once in another direction, and they get knocked out. This is kind of the central feature that makes this whole thing work. And so using this, actually, so with this boundary map, you can actually identify all these topological features. So topological features, so a hole, if you look at what a topological feature is, like a hole, like this hole, the 2, 3, 4, 5, 6 hole. Oh, let me just say one boundary map. Note, note the boundary of a boundary is 0. This is a famous feature. Boundary is 0. If I have something that doesn't, that I take the boundary of a thing, the boundary doesn't have a boundary. So now what is a hole? A hole is something, it doesn't have a boundary. So if I go around this right here, okay, there's no boundary. The boundaries are these each point. So when I go to 3 to 4, I get 3 plus 4, 3 minus 4, plus 4 minus 5, plus 5 minus 6, plus 6 minus 2. All of those points cancel out. A hole, or more generally a void or a connected component, it doesn't have a boundary. So doesn't have a boundary. So if it corresponds to a vector such that dk of this vector is 0, doesn't have a boundary. Boundary is no boundary. Now, of course, there are plenty of things that don't have boundaries. Like, for instance, the boundary of this simplex, if I look at this right here, and if I took its boundary, that would be 0, 2. So a hole has another feature, which is the two features. It doesn't have a boundary, and it is not itself a boundary. Why? Because it's the boundary of the hole, right? This set of simplices, this chain of simplices around here, is the something which is not in the complex. It's the boundary of the hole, the surface of the hole is something, each hole has a surface, the surface is boundaryless, and it is not a boundary. And everything that is boundaryless and not a boundary is a topological feature of this. All right? And then that's pretty much it, because in fact, so I should actually say that what this means is that dk minus 1 dagger acting on V does not belong to the simplicial complex. I'm just writing down the math part of it, but that's just the mathy way of saying we're looking for things that are boundaryless and don't have boundaries. And these are just the holes, gaps, voids, cycles, et cetera, in the data. These are the topological features of the data. It's what's called the homology of this data. Okay, and so now what one does, now it's just, you just use linear algebra. To find all vectors such that, dk is 0, but dk minus 1 dagger of v does not belong to the complex. In fact, if you really want to know, you construct what's called the, which maybe you don't, you construct what's called the combinatorial Laplacian, which is this object. And you look for things that are, these are things that fall in the kernel of this combinatorial Laplacian. Yeah?
This operator of this matrix orthogonal? Is that what you're using a dagger instead of a line?
It's not even square on its own, right?
Like it
Maps k simplices to k minus 1 simplices.
This one is
It's a very high dimensional sparse. This is this thing that we actually operate with, very high dimensional sparse square matrices. So dk operates from the space of k simplices into the space of k minus 1 simplices. It actually goes to a different vector space. Okay. So anyway, that's how these algorithms work. I mean, this is, I just told you, how does it, let me just summarize how the algorithms work. It looks hard to do. It's got all kinds of fancy words, but all that's happening is you find topology by constructing these simplicial complexes. Now you say, hey, I want to find the topology of this simplicial complex. And you do that by this trick of algebraic topology, and the trick is you map each simplex into this high-dimensional vector space, which I did in this case by quantizing it, okay? And then you just diagonalize, some suitable linear operator on this high-dimensional vector space. And the suitable linear operator is made out of this boundary map. The boundary map was constructed to have this neat feature that it constructs boundaries of things. And this good for all these scales epsilon. You find that, like holes and voids and gaps that persist for long periods of time, and then that's it. Okay. So I apologize. I took a little more minutes than I thought to. It took more than 10 minutes, but I didn't take much more than 15. So are there any questions about this? I feel a little guilty about like saying, hey, look at this, bringing in algebraic topology, but what the hell? And also, I want to point out that it took me, I'm doing this partly because it took me 5 years to get over the hump of actually being able to read the papers and figure out what's going on. And actually, it's not so scary. It's not scary after all. Moreover, you can easily see for the quantum mechanical people here, you can easily see how you can actually, this gives you an exponentially better quantum algorithm because you're trying to diagonalize a very large dimensional sparse operator, and that you can do exponentially faster on a quantum computer than a classical computer. Up with this kind of thing. But the point is that you can identify the topology, and that's what the classical algorithms do as well. Yeah?
Can you say one more time why the pattern of pluses and minuses in your bottom line and the top board makes sense?
Yeah. So remember, the rule is oh yeah, I think maybe you're right that I kind of screwed it up. Let's do it right. Right. So it's plus 2, 4. I omit 1, right? Thank you very much. I feel very embarrassed. Not only did I put math up, I got it wrong, which is typical for me, right? And then I have minus 1, 4. Second one, I omit the 2. Okay. And then for this one, then I omit the 4. So I have plus 1, 4. And then for the next one, I start with 2. I have minus 3, 4. And then I add, minus 3, 4. Then I add, so this is a tricky thing here. So I have the plus 4, 2, but I have to keep track of the orientation. So this really was 2, 4 in that direction. This is 2, 4 in the other direction. And then when I switch the orientation, I get a minus sign. These are actually oriented simplices. So not only is your question an excellent one, but you forced me to admit more of especially the math that's actually going on. And then the last one is plus 2. But because of the simplex, this point gets evaluated in one direction in one way and always the other direction the other way, so it always cancels out under the boundary. Thank you very much. You were so right. All right. So let me actually, I should get done. So actually, I think it might be time to say why I think this is an argument for this quantum order effect, which is that, we have these thought processes going on in the brain. They have a topology, right? Moreover, people write papers where they analyze the topology of the brain and the brain on drugs. By the way, my colleagues are analyzing the LSD data right now, as it turns out. See if the topology of your brain on psilocybin is radically different from the topology of your brain on LSD. My guess is it's still. So, you know, independently of what's actually physically going on, if we make a topological description of the brain, we have this sequence of vectors. We go through these different topological sequences. We have different connected components. We can describe at each point the topology of a brain by the evolution of a vector in a high-dimensional vector space. So, you know, this is just in the mathematical description of what's going on. And then, so we have just some vector that's more. I'll even make it quantum like this. So here is my, here's my vector. It's a function of time. It describes the topology of the space. This, you know, this mathematical description is there whether one wants it or not. All right. And then the real question is if the probability of falling into, you know, another vector, if the probability of A given V of t is equal to some function of this overlap between them. And I argued in hand-wavy terms before, this does make some sense, right? You know, if the answers to question B or not B are some attractor, there's a topology for this thought process, there's a topology for that thought process, it's described by some big vector. And here's my initial thought process after I gave the answer A for the first one. And if this complicated nonlinear process of the evolution of these vectors happens to have that the probability of going to B is proportional to the distance between these vectors, just the ordinary vectorial distance between these vectors, or some function of the distance between these vectors. All it has to be is a function of the distance between these vectors. Then you get this quantum question order effect. So just to summarize, because I have time, I brought up the quantum question order effect. It's a kind of a weird thing because it says quantum mechanics makes very specific predictions for how probabilities of questions asked in different orders come out. And there's empirical evidence from many studies on people that people obey something very similar. I actually recommend these papers, some of the papers that give you some of the more funky things like the probability of A and B being greater than the probability of A being less than the probability of A and B. You know, this is hard to imagine how it works, but it works out quite nicely in this when the A and B correspond to non-commuting measurements. I argued that, then I said, okay, and I argued that, well, maybe we can understand this quantum question effect by looking at algebraic topology, looking at topological analysis of the brain. Why? I mean, the quantum question order effect seems, weirdly, it seems like there's some weird vectorial linear algebraic-like process going on inside the brain. That's what it suggests. I have no idea if it's correct or not, I mean, but the data does suggest that. Where could this funny linear algebra exist? Well, because I was already doing this, I said, hey, you know, I'm doing this for the purpose of making a quantum algorithm. You know, there's the topological descriptions have an implicit, in fact, actually rather explicit linear algebraic structure to them. And if we, you know, in which the topological state of the brain is described by some vector in some huge honking dimensional vector space. And as that thought process evolves in time, this vector evolves in time. So if it is the case that, you know, as I said before, that somehow these probabilities for falling into this attractor are proportional to, you know, the overlap between these vectors, or some function of the overlap between these vectors, then to go. And of course, I already had to confess my other motivation, which was that we have a lot of data about brain function. We're going to have oodles more data about brain function. We're going to have to apply big data analysis techniques. There I mentioned big data. Yeah, the other reason for you know, you get the way to get grant proposals these days is to have it either big data or graphene in the title. So with our quantum algorithm, we could have a grant proposal that's, you know, graphene-based quantum random access memory for the analysis of big data, right? That was a sure winner. Anyway, I think that, to make sense of what's going on in the brain, which is very mysterious, certainly very mysterious to me, and not only because I'm more ignorant about that than most of the people in this room, but just it is mysterious. I think it's important to actually look at different ways of looking at what's happening in the brain. It seems to me that this kind of topological analysis might be helpful. So, thank you all for sitting through this, correcting my mistakes. That's you get extra. If this were a class, you would get an extra 5 points on the final grade for that one. And that's it.